Hello everybody, I'm Hajjar Ftouchi, a PhD student in supervision between two universities, Nantes University in France and Abdelmalek Saadi University in Morocco. So my work is entitled Improvement of α-sexithiophene Fullerene Binary Planar Heterojunction Solar Cells using a double anode buffer layer. During my presentation, I will follow these outlines. So first, a general introduction and aims, then organic solar cells principle and carrier charge generation process. After that, the deposition process and the characterization of the binary planar heterojunction based on α-sexithiophene Fullerene materials. And after comes the presentation and the discussion of the obtained results on the effects of molybdenum trioxide, copper iodide on the device performances. At the end of my presentation, I will draw some conclusions and give some perspectives. As you know, that energy plays a very important role in the socio-economic growth and the energy security of a country. Most energy is drawn from the fossil fuels like coal, oil, and natural gases, which is the consequence of energy and environmental crisis, natural resource exhaustion, and greenhouse gases emissions. So there is some alternatives which are green and renewable, like wind energy, biomass energy, hydropower energy, solar energy, and especially photovoltaic energy. Because every 40 minutes, the sun provides the humanity energy needs for 1 year. So for these reasons, our project is interested on photovoltaic solar cells, but especially on organic solar cells. So the evidence question is why organic solar cells? Actually, organic solar cells provide a unique opportunity as a next generation photovoltaic technology due to their lightness, flexibility, low cost, semi-transparency, and also they are visually pleasing. But on the other hand, they have limited efficiency and lifetime. For these reasons, they know a continuous progress, as it's seen from this updated Enrich. Organic solar cells consist on at least two active materials, electron donor and electron acceptor, sandwiched between two electrodes with different work function. Actually, usually the active materials are organic semiconductors, polymers in the case of bulk heterojunctions, and small molecules in the case of planar heterojunction. And the charge generation process can be split into 4 steps. The first one is the photon absorption and the exciton generation. Then comes the exciton diffusion to the interface. So here comes the exciton dissociation. And after that, the carrier charge transport and collection. Electrons to the cathode and holes to the anode. Planar heterojunction organic solar cells based small molecules such as α-sexithiophene have been significantly improved. The maximum power conversion efficiency reached until now on planar heterojunction is 8.5%, using 3 small molecules where the α-sexithiophene is the first absorbing material and the PLDSS as the whole transporting layer, in the layer inserted between the donor and the anode material in order to reduce the energy barrier between the HOMO of the donor and the work function of the anode material. In the same study, we have also studied the binary structure and the maximum power conversion efficiency. It was 1.03%. So the both structures they have used PLDSS as the whole transporting layer, while this material is highly hygroscopic and acidic, so which affects the lifetime of the device. So in our current study, we are interested to the enhancement of this device, which consists on the indium tin oxide material as the anode, molybdenum trioxide or molybdenum trioxide copper iodide as the whole transporting layer, α-sexithiophene as the donor material, Fullerene the acceptor material, and Al-Q3 as the exciton blocking layer, and at the end, aluminium as the cathode material. So the goal of this study is the investigation on the effects of copper iodide on the structural, morphological, and the optical properties of α-sexithiophene in order to enhance the photovoltaic parameters of the device. So let's move now to the deposition process and the characterization of the binary planar heterojunction solar cells based on α-sexithiophene Fullerene. So this diagram represents the elaboration process and characterization. So the first step is the substrate preparation by etching 30% of the ETO surface, chemical cleaning and heating at 80 degrees Celsius, loading into a vacuum chamber. Then comes the thin films deposition using vacuum sublimation, and we control the thickness and the growth rate by in situ using a quartz microbalance. The third step is the cell's characterization using oil solar simulator. So now comes the presentation of the sum of the obtained results on the effect of molybdenum trioxide copper iodide on the device performances. So this figure represents the GV characteristics in dark and enter elimination of our elaborated cells using copper iodide molybdenum oxide as the anode buffer layer and using molybdenum oxide alone as the anode buffer layer. So this table represents the values of the PV parameters of our cells. So we can show that there is a huge enhancement in the open circuit voltage, in the short current density, in the fill factor, and by consequence the power conversion efficiency. So it's difficult to explain that. For this, we have done some analysis on the α-sexithiophene material deposited on molybdenum oxide alone, and another sample of the α-sexithiophene deposited on molybdenum oxide copper iodide, and we have done some analysis. X-ray diffraction, UV visible spectrometer, atomic force microscopy, and scanning electron. So in summary, we can say that the optimization of the morphological and the optical properties of α-sexithiophene material using medium speed rates of 0.04006 nanometer per second, and the optimization of the thickness of the donor material using 22 nanometer. Also, the optimization of the HTL material, the whole transporting layer material using a double anode buffer layer, molybdenum oxide, copper iodide, leads to achieve an efficient device based on binary structure with a power conversion efficiency of 1.70%. While aiming to increase the absorption of the active layers by the optimization of a ternary device using an ambipolar material between the acceptor and the donor material. So I would like to close my presentation by some acknowledgements to the Centre National pour la Recherche Scientifique et Technique, PHC Maghreb Topkal Franco-Marocain, Campus France, Centre National de la Recherche Scientifique en France, et the EVE International Renewable and Sustainable Energy Conference. Thank you for your attention.